Hi, this is Mrs. Baston, and today we're going to talk about quantum mechanics, which is section 6.5. So up to this point, we've been talking about the Bohr model of the atom. So Bohr said that the electrons were found in two-dimensional orbits, and they could only go from one level to the next in these allowable orbits when they gained energy or when they released energy. Erwin Schrödinger came along and modified Bohr's model a bit by developing a mathematical treatment to try to figure out where the electrons were. So his model also takes into account not only the particle nature but also the wave nature of matter. So this is known as quantum mechanics. So he also developed something called the wave equation. When you square the wave equation, it gives you a probability density map that you can see on the right there. What that tells you is where there is a high concentration of dots, that means there's a high probability of finding the electron in that region. So if you remember again from talking about the Heisenberg uncertainty principle, is that you're not always going to know exactly where the electron is. You can only know the most probable location. So this electron density map kind of gives us an idea of where the most probable location is. When you solve the wave equation, it gives you a set of wave functions or orbitals and their corresponding energy. So each of these orbitals describes a spatial distribution of density, and it can be described by a set of three quantum numbers. So before we start talking about the quantum numbers again, let's look at, again, just the difference between Bohr's orbits and Schrödinger's orbitals. So Bohr's orbits were two-dimensional. The electron traveled around the nucleus in these allowable orbits. Schrödinger's model gives us these orbitals, which are three-dimensional regions of space. So Bohr's model, if you looked in the orbit, you would find the electron, whereas Schrödinger's model, this is just the most likely place where you might find the electron. Okay, so let's go through and look at the quantum numbers. So the first quantum number is very similar to the energy levels of Bohr. So it's notated with an n, and this describes how far away from the nucleus the electron is. So n equals 1 is going to be very close to the nucleus, n equals 2, n equals 3, n equals 4. The bigger the value of n, the further away from the nucleus, and also the more energy that electron would have. The next one is called the angular momentum quantum number, and it's notated with an L. What this tells us is the shape of the orbital. So this is where we talk about the s orbitals, the p orbitals, the d orbitals, the f orbitals. So let's just write a little note here that says these are now notated with numbers as well as letters. So before, when we learned this, we talked about the s orbital, the p orbital, the d orbital, the f orbital. So now what we can do is we can say if it's an s orbital, we say it has an L value of 0. If it's a p orbital, it has an L value of 1. A d orbital has an L value of 2, and an f orbital has an L value of 3. So those letter designations communicate the different values. So s we now call 0, p we call it 1, d is 2, f is 3. Okay, so this is what we just wrote on the previous screen, S0, P1, D2, F3. The third quantum number that we can use is called the magnetic quantum number, and this is notated with M sub L. So what this tells us is the three-dimensional orientation of the orbital. So in the next set of notes, we're going to look a little more specifically at what these different shapes of the orbitals are. But these are notated with M sub L, and the values are integers ranging from negative L to positive L. So on any given energy level, there can be up to 1 s orbital, 3 p orbitals, 5 d orbitals, 7 f orbitals, and so on. So if you remember before, when we talked about this in Honors Chem, s orbital had 1 orientation, the p orbital had 3 orientations, the d orbital had 5, and the f orbital had 7. So to show that, again, if your L value is 1, for example, so if L equal, let's start with L equals 0. If L equals 0, then M sub L is equal to 0 because there's only one orientation. If your L value is 1, which is a p orbital, there are 3 orientations for the p orbital, so your M sub L could be equal to -1, 0, or +1. So each one of these numbers stands for one possible orientation. Okay, so here's a chart that kind of summarizes all those things that we just talked about. So at the first energy level, we only have s orbitals. Okay, so at the first energy level, that's the closest to the nucleus. So if this is the nucleus, then this would be n equals 1. That would be our first energy level. The subshell designation, 1s, tells us that the first energy level, that's our s orbital. The possible values of m sub l, that's our orientation, how many different ways can it be on the axis. The m sub l value is 0 because there's only one possible orientation. Number of orbitals in the subshell, and again the subshell is the shape and the orbital is the orientation, so let's write that on here too. So subshell, you could also say, is the shape, and then the orbital is the orientation. For an s orbital, there's only one orientation, so then the total number of orbitals is only 1. Okay, at the second energy level, now we have s and p's. So we have 0 and 1. 0 stands for s, 1 stands for p. The designations are 2s and 2p. The 2 stands for the energy level. The letter stands for the shape. The possible values, these are our orientations. There's one orientation for an s, 3 orientations for a p. This again tells you the orientation. So if you count those up, the total orientations are 4. Okay, now we're at the third energy level. Now we have s's, p's, and d's. So 0, 1, and 2 stands for SPD, 3s, 3p, 3d. The values of L, 1 orientation for the S, 3 orientations for the P. Now we have 5 orientations for the D. So if we count all those up, we have a total number of 9 orientations. And then from 4 and higher, we have S, P, D, and F. So 0, 1, 2, and 3, S, P, D, F. So 4S, 4P, 4D, 4F. S has 1 orientation, P has 3, D has 5, and then F has 7, if you count those all the way across. So total then would be 16. And then we're going to look at a little bit later on is that each one of these orientations will hold 2 electrons. Okay, so let's look at a question that goes along with this. So this first one says, predict the number of subshells in the 4th shell n equals 4. Okay, so at the 4th energy level, we would have s orbitals, p orbitals, d orbitals, and f orbitals. Okay, so the number of subshells would be 4 because you have s's, p's, d's, and f's. The label for each of those subshells, we would use the 4 to signify that it was at the 4th shell or the 4th energy level. So it would be 4s, 4p, 4d, and 4f. And then how many orbitals are in each of these subshells? That's how many orientations. So the 4s has 1 orientation, which we would designate with a 0. The 4p has 3 orientations, which we would notate with -1, 0, +1. The 4d has 5, so we would go -2, -1, 0, 1, 2, and the 4f has 7 orientations, which is -3, -2, -1, 0, 1, 2, and 3. Okay, so another way to look at this would be thinking of this as like the electron's address. So these quantum numbers tell us the most probable location of the electron. So the first quantum number, the principal quantum number, tells us how far away from the nucleus could this electron be. The second one tells us what shape of an orbital are we looking for, and then the third one tells us which orientation of that particular shape would we look to try to find this particular electron. Okay, so we're looking at what is the designation for the subshell with n equals 5 and L equals 1. Okay, so the n equals 5 tells us the fifth energy level. And then the L equals 1 tells us the shape. So remember we said S was 0 and P is notated with L equals 1. So this would be the 5p subshell. This then says how many orbitals are in this subshell. So we're looking for how many orientations. There would be 3 orientations. And then the value of m sub l for each of these, because there's 3, we would do a -1, a 0, and a +1. So again, each one of these numbers stands for a different orientation of that particular subshell.